Okay. Just in case it was corrupted. Okay, what does a plus error mean? What does a negative error mean? All other things being equal compared to the value it otherwise would have been. So if A is connected with B with a positive link, does that mean if A goes up, B goes up?
Yeah. Yes.
No. No, not necessarily.
Not all other things are equal.
And no other paths.
If nothing else is affecting B.
Still not fully.
There could be other paths that.
No, still not tight enough. So I need to sharpen this because it's ambiguous. And the reason it's ambiguous is you need to ask me, does it go up relative to what? So the danger here is if I say, if A goes up, does B, if A is connected with B with a positive link, if A goes up, does B go up over time?
Proportionate to A.
No. Good guesses, but no. It's, so ladies and gentlemen, if A rises, that doesn't mean that B will go up over time. It means that B will go up relative to the value it would have had if A hadn't gone up. So B may still be going down over time. A rises, and B is still going down over time. But it's going down less quickly. Or it's at a higher value than it would have been if A had been lower. Do you appreciate that difference? Look, if A goes up over time, for example, it doesn't mean that B will rise over time. It means that B will be a higher value than it would have been if A hadn't gone up. B may still be dropping, but it'll be dropping less quickly, or it'll be still a higher value than it would have been if A hadn't gone up. This is a big difference. Big difference. There's many cases where A goes up and B is still going down. Think about this. So we have a stock, and 1,000 people per day are leaving the stock, and 100 people per day are coming in. Now we increase the inflow from 100, so 1,000 per day are leaving, 100 are coming in. We increase it from 100 coming in per day to 200 coming in per day. Does the stock go up over time? No, it's still going down. The outflow is greater than the inflow. It's still going down over time. But its value is higher than it otherwise would have been. Because there's 200 people coming in per day rather than 1,000. And that flow, the inflow, sure as heck has a positive connection to the stock. The inflow has a negative connection back to the stock. We increase the value of the inflow, it increases the stock value, but it increases it compared to the value it otherwise would have had. Does not increase it necessarily over time.
Would it be accurate to say like just the rate of change will increase?
Yeah. Yeah. For a stock. For a stock. That's right. That's right. Yeah. For a stock. There's actually a very precise mathematical definition, which is, partial x partial a is greater than 0, meaning if A goes up, it'll bring x's value up relative to the value it would have had with the original value of A. But that's an important distinction. That's why I say all of the things being equal, meaning all other pathways are held the same. An increase of the first variable will increase the second variable above what it would have otherwise have been. Okay? Man, I don't get any of these things. I go between a feeling that, okay, now I'm in trouble because I got to know, and
and a feeling like, oh, that would be a really good question. Maybe I should add it. Neither of those is necessarily bad sentiment for you, I suppose. But okay. Are negative feedbacks bad?
No.
Give me a negative feedback that'd be good.
Brushing your teeth and keeping down cavities.
Good man. Yeah, I like it. Give me a negative feedback that can be bad. Addictions,
So
yeah.
the less you do it, the more you want to do it, and then it will regulate.
Right, exactly. It'll sort of regulate back into the state of taking the opioid or whatever, because you feel more and more craving, you take it, and it'll bring you back into this state of sort of adverse equilibrium. Okay, how about a positive feedback? Are all positive feedbacks bad? Give me a positive feedback that's adverse, that's unpleasant, or that's not good. Spread of flu, right? That's not good. Spread of contagion, yeah. Okay, give me a positive feedback that people spend massive amount of time, money try to achieve. That they consider good for them. Or that you consider good for you, probably.
Reproduction.
Far be it for me to stand in the way. That's not a bit. Each his own. So fair enough. Yeah, I can't dispute the fact that a lot of people share your sentiment. Sure. Helping a bank account grow, right? You want it to grow quickly, or an investment grow quickly, or you want your product to be bought and talked about so more people will buy it. I mean, there's all sorts of times we try to get instability. We try to lead to positive feedback. So don't think positive is good, negative is bad, and don't think positive is always bad. Far from it. So positive feedbacks are associated with unstable behavior, divergent behavior, rapidly growing. Why does it rapidly grow like this?
Because it's positive feedback, so therefore it's exponential.
Yes, yeah. So if we think about it, a feedback involving a stock, and we think about like a prototypical positive feedback, here's X, and this is the flow into X, F. If we think about, okay, if this is a positive feedback, then we have sort of positive on both of these. This is associated with a sort of flow F, so F has a positive link to X, and X has a positive link to X. So there's a complete cycle here that's positive. In its most basic form, we could write this as, okay, the flow is approximated by alpha times X. So we have, X dot equals alpha times X. And what is that if we solve it? What is that? Speak on as if all of one voice. What is this? What is the solution to this? Anyone recognize that? I'll give you a hint. It's not far from my head. Well, it's a very close relative.
E to the
Yeah. E to the alpha t. Ladies and gentlemen, so if the flow is positively, so alpha is positive, portion of the stock. If the stock increases the flow and the flow increases the stock, and all feedbacks have to involve the stock and the flow. You might say, well, the flow doesn't depend linearly on the stock, but if in the first approximation it's linear, you directly get exponential behavior. So, X increases, it leads to flow into it, T increase leads to even more increase in X, and it just, more leads to more, leads to more, leads to more. Much like, as the gentleman said, in reproduction, where one leads to, one leads to two. Two leads to four, leads to 8, leads to 16. Right? Okay. Negative feedback. ladies and gentlemen. Stability. Where did we get this mathematically from? Speak on, as in one voice. Where does that come from? Oh, it's right here. The Boolean system eventually get back to the original state. So look, this is like the prototypical simplest negative feedback. The outflow depends linear on this. And what does this lead to in terms of behavior? Yeah, e to the minus alpha t. And if there's an inflow, it'll go up. If there's an inflow, it'll go up to some equilibrium value like this. Okay? It'll approach some equilibrium value. And oscillations. We started like this. If you have coupled feedbacks, you can get this sort of behavior. Okay. Oh, first order delays. So with different levels of delay, you get different levels of convergence. We talked, okay. I'm hitting most of the big things. I want you to know infectious disease models. So ladies and gentlemen, if we have an infectious disease model as a closed population, no one's coming in, no one's leaving, classic SIR model, and we start a disease spread in that model, let me ask this question. Is it always the case that an outbreak occurs? That you get a sudden rise and then an eventual fall?
Depends on the initial state.
Okay, it depends on the initial state. Suppose everyone except one person starts susceptible. And the other person starts effective.
Depends on the recovery time. They might recover before they can infect others.
Good. It depends on the basic reproductive number. What is the basic reproductive number? Basic reproductive constant.
Number of people you infect while you're infected.
Yeah, before you recover. The total number of people so basic reproductive number is in a situation where basically no one else is infective. So here everyone is susceptible. Okay? You're surrounded by susceptibles. How many people do you recover? How many people do you infect before you recover? Suppose that's greater than 1. What's going to happen? An outbreak will happen. Suppose that's less than 1. What will happen? It'll die out. Ladies and gentlemen, if an outbreak occurs, does everyone in the population get infected? Why not? What's the throttle? What prevents them from getting infected? So the answer is no. What's the throttle? What prevents them from getting infected?
Connections.
Okay, yes, connections. Ultimately, what prevents them from getting connected is the fact they're surrounded by too few what? Susceptibles. If there's too few susceptible, they can't spread it efficiently, ladies and gentlemen. It'll peter out. Okay? And so once the infection spreads, it's self-limiting. It spreads in this closed population. It's burning up its fuel, and at some point the fire will die out because it can't spread efficiently. It has to go longer and longer before it can infect even that one person. Eventually it can't, and it dies out. And there'll be some wood left over, unburned. Not everyone is going to get infected. Sometimes it's a large part of the population that's left over. Sometimes it's a small part, but it will be left over. Infection will essentially go to 0. Well, there's still people who are susceptible. Suppose it's an open population. What happens then?
You could have a sustained.
Good. You could get a sustained equilibrium. Alpha will approach it with oscillations and it will be sustained. What is the fraction in that sort of situation where you get a sustained equilibrium? We examine the case. What's the fraction that remains susceptible? Does anyone remember? It's beautiful. the fraction?
Does it have to do with the contact rates and the time they get infected?
Yeah, and that's 1 over R0. It's 1 over the mean number of people infected would infect before they recover in a population that's otherwise susceptible. And it turns out that that's sort of the fraction of infectives that's needed to keep it in equilibrium. Suppose that it's less than that. What will happen? Suppose the fraction of susceptibles is less than that, like your vaccination. What will happen? If I vaccinate enough people, so there's not enough people, there are fewer of this fraction, what's going to happen?
It'll die out.
It'll die out. So we need actually, with vaccination, we need 1 minus 1 over this fraction vaccinated, more than that fraction, so that we can prevent it from hang on. What is R0 in a model? So think about what are the key parameters in an infection spread model. So here we have SIR. What is this key formula here? I wrote it on the board earlier. What in the other room? What is it?
Contact rate times
Yeah.
probability of infection times the infection ratio.
Good. So I'm going to write it like this. Ladies and gentlemen, I want to make sure you remember the intuition for this. This is the number of people per unit time getting affected. So S is the number of susceptibles. Each susceptible has contact with C people per day, total. Of those, C times I over N is the total number of people they have contact with per day that are what? Infected. And for each of those, they have beta chance of getting infected. So this is kind of a total approximation of total probability of them getting infected. And what did we call this term?
Force of infection.
Force of infection. So this is S times the force of infection. Is this term here. Force of infection is a hazard rate. It's a chance per unit time. It's not fixed. Is it fixed in this model? No. It depends on value of I. More people that are infected, the higher the force of infection. Ladies and gentlemen, and suppose that we have further a recovery rate of I over tau. So a number getting recovered of I over tau. So we have average time T till recovery. An average time T that they spend infected. What is R naught? What's the basic reproductive number? How many people will an infective infect in an otherwise, in a totally susceptible population? Well, let me rewrite this another way. Not thinking I'm giving too much away. All I did is I exchanged the beta, the I and the S term. Now it's written from the perspective of an infective. I'm going to give an infective, this is the number of people right now that I infect per what? Yeah, per unit time. In fact, I have contact with C total people, of them, C times S over N are the number that are what? Susceptible that I meet per day, and each of them I have a chance of beta to infecting per day. So C times S over N times beta is the number of people per day on average that I do what to? Infect. Now, if I'm in a totally susceptible population, then how can we simplify this? This term.
S over N is 1.
S over N is 1. Basically, okay,
I'm one person that's affected, but suppose there's a million, we have 1,999,999 people. So basically this is 1. So it's C times 1 times beta, or what? C beta is the number of people I infect per unit time. How long am I infected? Time. So what's the total number of people that I infect?
C beta tau.
C beta tau. That is R naught, ladies and gentlemen, for that simple law. That's the total number of people I infect in an otherwise susceptible, in a totally susceptible population. Now, I distinguish that from the effective reproductive number, which is the total number of people I infect before recovery in an arbitrary state, like not everyone is susceptible, and that is just this times S over N. So if S over N is, if it's, that's beautiful. Gosh, I would hope maybe people would shout out, shout out with enthusiasm. Wow, it's just great. Ladies and gentlemen, do you see why it's beautiful? I guess not. Okay, ladies and gentlemen, this is R naught. If we consider the effective reproductive number here, what is the effective reproductive number? It's the number of people I infect in the current situation, even though not everyone is susceptible. In the current situation, how many people do I infect? I said it earlier. What's the value for the basic reproductive number? For the effective reproductive number, R star. What is it? How many people do I infect if not everyone around me is susceptible? Speak on as in one voice.
CS over N beta.
C S over N beta times, but how many people do I infect before I recover? Times tau, right? Okay, now, ladies and gentlemen, I'm going to arrange this, just don't mind me. I'm just going to I'm going to rearrange it to be S over N times C times beta times tau. Okay, that's S over N times R naught, right? And I tell you that at equilibrium, when it's in balance, the fraction of people that remain susceptible is 1 over R naught. Why does that have to be the case? Suppose that the fraction that are susceptible is 1 over R naught, right? This is the fraction that are susceptible, S over N, right? Right? That's the fraction that are susceptible. So I tell you, when it's in balance, when it's in endemic equilibrium, when it's in this sort of balance of endemic equilibrium where the affection is staying constant, then this value will be 1 over R naught. That's the fraction that are susceptible times C times beta times tau. Now what is 1 over R naught? It's 1 over C times. Okay, so this is 1 over C times beta times tau times C times beta times tau. And what is that? 1. So in equilibrium, in the situation of equilibrium, each infectives infects how many people before they recover? 1. They replace themselves, ladies and gentlemen. So it doesn't go up or down. If they were infecting more than 1, it would be going up. If they infected fewer than 1, it would be going down. So they exactly replace themselves in endemic equilibrium. It has to be the case. And it's just awesome. Maybe I should ask about that. It's beautiful. It's got to be the case. If you've never enjoyed the pleasure of this intellectually, there are certain times in scientific education where suddenly a whole set of facts that you've known through different quarters, they all just suddenly make sense, and you understand why one has to be the case from the others. And you can forget large portions of it just arrive on, because you know everything that points to that, it must be this way for it to all fit together. And it's gorgeous, and it's great. And I hope someday it will happen to you. You may differ in your hope. After all, look what it did to him. Believe me, trust me. Just one more time, okay? Anyway, infectious disease models. Differ for dynamic. Ladies and gentlemen, it's the fraction that are susceptible that constrain the spread of infections. When it's too low, it can't spread. An infective can't spread it to enough further people, okay? So you should be able to create a state space. You should be able to talk about dynamics of first order delays. You should be able to determine locations of equilibria. You should know so you should know that you can determine stability and what what it means for it to be stable and unstable, but I'm not going to ask you to determine stability of a system. I'm not going to ask you to determine the eigenvalues or eigenvectors. Maybe next year I will. And I want you to have some understanding of the intuitions for what it means there's multiple equilibria. Oh, well, yeah. So here, for example, we solve for two cases where gophers and coyotes equal 0. This is solving for equilibria, right? We're solving for the equilibria of this system, where gophers and coyotes are not changing. What that means is both stocks, the rate of change is what? 0. That's the definition of equilibrium. And very commonly, there's two cases. One is sort of a trivial case where we have some specific criteria, like the number of gophers is 0, and therefore, by definition, the rates of change of gophers is 0, and we derive coyotes have to be 0 as well, because coyotes can't be eaten. Alternatively, we will often have a case where it's not so obvious, and we'll actually solve for an equilibrium here. So this is case 2, where we're solving for G and C where these things equal 0, but since we know G is not equal to 0, we solve for the G equals 0 case for case 1, and for case 2, because we know G is not equal to 0, we can divide both sides by G. And that allows us to then solve for C here very nicely, and then we substitute in for C in the other equation, and we can solve for G. And things are beautiful. And this leads to two equilibria. And in state space, these equilibria occur in state space. One occurs with coyotes, gophers both being 0, and the other occurs with them having exactly some number. And it turns out that if you look at the equilibrium, the stability of the equilibrium, what's really interesting is there's what's called a limit cycle around here. Okay? So it actually goes around this point in cycles. Okay? It'll cycle around this point in kind of a circle. And that's why we see periodic behavior with it. It keeps on coming back to its point in state space. It's great. And so the key thing here, ladies and gentlemen, I'm trying to speak to people with different levels of understanding here as normal, but the key thing here is that you are solving the system. You're trying to get solve for values of the state variables, the stocks, setting all the derivatives simultaneously to 0. Please do not think, in one case you set this one to 0, and the other one you don't know what its value is, and the other one you set this derivative equals 0. No, for each equilibrium you need all of the derivatives set to 0. They have to, because then it's only then the system's in balance, all in balance. So in determining the location, you are saying we're trying to solve for the state values of state variables, here G and C, for the particular case where C dot and G dot equal to 0. That's what we're trying to do. And it turns out there's 2 possibilities for that. And that's often the case. There's more than one possibility. Rarely would I give you one where there's more than 2. Now, the key point is you're trying to solve for G and C in terms of what? What should be on the right-hand side? You get back a value for G and for C. What's on the left-hand side? G equals something. What should that something involve? What should that something involve? No. So if you solve this whole thing and you have G, I solve this whole equation, I have G equals something and C equals something. What's over here? No. What's over here is constants, parameters, things like alpha over beta, something like that. It's the or numbers. It's the number. So here, the solution is alpha over beta and gamma over delta. Those are the 2 values for when G is not equal to 0. The other possibility is G equals 0, in which case C equals 0. That's 2 numbers on the right. G 0 in both cases. Okay. So, ladies and gentlemen, this is what we're solving for. We're solving for the values of the state variables for which will make the derivatives, all the derivatives, equal to 0 simultaneously. Because we want the system to be in balance. The criteria is we're solving for the values of G and C where the system will be in equilibrium. By definition, the system in equilibrium has all the derivatives equal to 0. And that's what we're seeking to determine. What are the values of G and C when they are all equal to 0? Okay. Any questions about that? Okay. Discrete event modeling. Entities. What are entities? Speak on.
The objects that flow through the
Yeah.
discrete event model.
Yeah, the entities that flow through this workflow depicted in the discrete event model. Any logic sometimes calls them agents. But the fact is they're often passive. What do I mean by passive?
They don't have agency.
They don't really have agency. They typically they just are operated upon by the processes. They wait in line. They go through delays. They seize resources and they release resources. I'm tempted to say they take exams, but no. They pass through these processes. They're sorted and diced and flow into things, batched up, etc. They're fairly passive compared to an agent-based modeling. So traditionally they've been known as entities. They could be cars, they could be widgets, they could be pieces of paperwork, they could be people. But they're typically more passive. Give me an example of 3 types of resource, or tell me about 3 types of resources in any logic.
Mobile.
Okay, static. Give me an example of a static.
MRI machine.
Good, MRI machine. Give me another.
Portable.
No. Well, okay, that's another category, portable. But another example of a fixed one or static one is a room, right? Like a procedure room or a room, an operating theater or something. It can't be moved. There's portable, which can be moved, but has no agency. It has to be moved by someone. And the third one was mobile, things that can move around. Give me an example of mobile. A nurse, a doctor, a physiotherapist, etc. So these kind of flow paths, these work paths, when do queues arise?
When a resource is busy.
Yeah, when a resource is busy. You're waiting for the resource. How do entities interact in the model? Sorry? Yeah, they make each other wait because one uses a resource, the other can't use the resource. So in discrete event modeling, there's typically fewer things emergent than in traditional agent-based modeling, but there are some things that are emergent features. Frequently we capture movement endogenously, and the exact time it takes from someone to get from A to B is calculated in the model. So it depends on the vagaries of the route. Sometimes it might even, in principle, it can depend on congestion or where the resource is located right now, et cetera, where the patient happens to be. And they route their way around the routing network within the model. Other things are sometimes hard-coded, things like how long a given appointment takes, et cetera. Okay. I will say that from a certain perspective, agent-based modeling and system dynamics, aggregate system dynamics models, turn each other on their head. In aggregate system dynamics, the model is organized by state or characteristics of the people. It's broken up into units: susceptible, infective, recovered, according to what state people are. You can imagine susceptible men, susceptible infective men, recovered men, susceptible women, infective women, recovered women. Those are different states. People are the model's organized according to the state. And then each one of those states records the number of people in it. That's the data. In agent-based modeling, the model's organized by individual, and each individual keeps track of their state and characteristics. So it's kind of flipped. In system dynamics, if we want to have like aggregate system dynamics data on multiple cities, for example, we could do that. They'd be just different variables in the same model, not really in any sort of hierarchy. In agent-based model, we typically have nested relationships. So one agent could contain other agents or reference to other agents. Some big trade-offs here. I didn't cover it in class. My throat is horrible, and while I could cover this now, I feel I'd do a disservice to you keeping it longer. There's videos where I cover this in extensive detail. Just suffice it to say there's real trade-off when it comes to representing models in an individual-based or aggregate way. There's lots of trade-offs between them. We've covered some here. Running time. Why do agent-based models, if you want to calibrate an agent-based model, why does it require more time than an aggregate system dynamics model?
So it runs slower.
Sorry?
It runs slower.
Yeah, why does it run slower?
The bigger it is, the longer it takes to calculate.
What's that?
Like the scalability of it.
Yeah, okay. So as we double a population size in an aggregate system dynamics model, how does the runtime of that model rise? Suppose we have an SIR model in stocks and flows. Suppose we go from it simulating 100,000 to 1 million people. How much does it slow down? It doesn't at all. It's just bigger numbers. It's not like the computer, wow, that's a big number. It's in agent-based models, if you go from a population of 100,000 to 1 million, could it slow it down? Yeah, it could really slow it down. You could also get the message saying you have to buy the professional. Believe me, been there, done that. So yeah, it makes a huge difference population size-wise. So in general, there's more moving parts in an agent-based model. But give me another reason why typically to get robust results, to get robust findings out of a model and to calibrate a model, it takes a lot longer, besides just the run of each run.
Because you might need to run agent-based model often, more than once to see a trend.
And why is that?
Stochastics.
Because it is stochastics. It typically requires running it again and again and again, what's called Monte Carlo ensemble. We're running it many, many times to make sure we're not seeing flukes, to make sure we're seeing real robust findings here. It's not just a happenstance of chance, okay? So there's lots of trade-offs there. Let me ask this. If you were to double, so we didn't really talk about this that much, but I did allude to it. If we were to double, suppose now in a system dynamics model, that one we want from 100,000 to 1 million population. Suppose now we say, oh, we don't want to just have total susceptibles, infected, recovered. We want to have susceptible men, susceptible women, infected men, infected women, recovered men, and recovered women. How will it affect the running time if we want to keep track of just a factor, that aspect of heterogeneity, that aspect of characteristics? How would it affect the running time?
An agent-based?
No, in system dynamics.
It will slow down because it's more stocks and flows.
Yeah, it's more stocks and flows. We basically double the stocks and flows. Not only that, I mean, this gives me the willies as a software engineer, but we basically need to undertake changes across the entire model just to capture the effect we want to capture, sex in the model. We have to go change each and every stock and each and every flow to be, over men and women separately, or make a complete copy of it, and so on. And now it basically slows it down by a factor 2. How about an individual-based model? How about an agent-based model?
It won't slow down at all because they're just in one
Yeah.
state anyway, so if you have double the states, it doesn't matter.
Yeah, I mean, that's right. So, okay, we just tag each person with a sex. I mean, we have an extra variable for each. It's minimal impact. So, with respect to heterogeneity, capturing more variability between people, agent-based model is much more scalable. With respect to population size, system dynamics aggregate model is more scalable. Keep that in mind. Keep that in mind. Okay. I want you to know, if you see a model like this, okay, forget about the square thing, but if you see a model like this, I want you to be able to create equations for it. You need to be able to do that. You need to be able to do that with comfort. You need to be able to go from this to this, and you need to know where these things come from. Like these two, why am I coloring these both blue?
It's the same flow.
Yeah, it's the same flow. That's one thing that's kind of awkward about this. It's not, it breaks down our levels of abstraction. This flow appears twice. Outflow here, inflow here. Right? Okay. So we want to capture that, right? I want you to be comfortable with that. So suppose something flows in from nowhere. So this immigration, suppose that flows in. Where does that go? Well, it comes in here. All it does is increase the rate of change of S. It doesn't flow out to anything. That's why it's shown as from this cloud. But it just flows into here, hence it's here. Why is it, if it were a minus associated with it, what would it mean? It would be an outflow to nowhere, no other stock. It would just flow out to nowhere. Okay. Okay. Yeah. Key points. I don't have time to go over this, but it's worth you looking at this. This dynamics of stocks and flows, ladies and gentlemen. What's going on as over time in a growth and decline? What is it that's going on? Like during this initial point, what's happening here? Why is this growing basically exponentially?
Lots of susceptibles.
Yeah, there's lots of susceptibles, and why does the number of infectives grow exponentially? because they're spreading very efficiently, right? It starts with 2 people, and they infect each 2 people, and it goes to 4, and it goes to 8, and it goes to 16, and it just goes by gangbusters because there's lots of susceptibles. It starts turning around. At what criteria is it flat here? Give me 2 specifications of criteria, both of which are true. Inflow equals outflow for the I stock. What would that mean?
Just as many as are becoming infected as they are recovering.
Yeah. The number of people per day, say, becoming infected is the same as the number of people per day recovering. That's one perspective. How about from an individual perspective?
Each infected infects one person.
Bingo! Each infected infects one infected before they recover. R star, this number of people infected by infective in this current state is what? 1. Yeah. And then it starts going down. Why is it going down so quickly after that peak? Sorry? Yeah, so first of all, the number of there's a decline in the number of infected. So as the number of infected goes down, the number of new infections goes down. More than that, the number of susceptibles is still going down. So you're getting this double whammy. The number of susceptibles is going down, and it's dropping this, and as the number of infectives further drops, it drops even more the number of people that are getting infected per day. And so the inflow is even smaller and smaller, and so it's really dropping. Put another way, though, what else is going on? So that's from an inflow side, but what else is going on here? So from an inflow side, it's going down fast because the number of susceptibles is dropping, the number of infectives is dropping. And that's leading to go down faster. But what is going on in the outflow? Well, there's still quite a few infectives. It's still dropping, but there's still quite a few infectives. And that means there's lots of what? Recoveries going on. So you got plenty of recoveries. You got slower and slower inflows. And you get more and more imbalance. It's just dropping. Woo! By the way, it's no accident. This looks like a what? What does this look like in the first part of it? Positive feedback loop. 1 to 2 to 4 to 8. What does this look like? Negative feedback loop. It's draining the number of recovereds. First order delay out of recovereds. Ladies and gentlemen, how would this look different if we had an open population?
It would reach equilibrium mostly.
Yes. And what equilibrium would it reach? What's the equilibrium?
1 over R.
Yeah, 1 over R naught is the fraction of what? Susceptibles. And another way to put it is what? R star equals 1. R star equals 1. Each infected infects exactly 1 person equilibrium. And ladies and gentlemen, that is exactly the point where if you look at the graphs, it's at exactly that fraction of susceptibles that the number of infectives will be reaching its maximum. It reaches maximum at the point where it's flat, where it's in balance. And that's, at that criteria, the fraction of susceptibles is such that it's 1 over 0 and each effective affects exactly 1. It's beautiful. It all fits together. It all fits together. And I hope for you tomorrow, it will all fit together. Okay? If it's any consolation, it'll be a 3-hour exam tomorrow. If it's any consolation, I spend historically 45 minutes to an hour marking each one. So I'll be marking long after memory break. Yes, I'll upload the slides and I'll upload the videos. Thank you. Good luck, folks. I'll see you tomorrow.